supersymmetric, holomorphic, and topological field theories in 2 and 4 dimensions.
Everything should be on now. Can you hear me? Okay, so I think my title has been very misleading. I suspect I'm never going to get to what I originally was thinking. Maybe, yeah. So let's just say a little bit. Last time all I wanted to do was give a definition of an elliptic Lie algebra on a manifold. And actually, the definition worked pretty, it's evident modifications of defined elliptic infinity algebra. And we said this will serve as a model for a formal elliptic derived moduli problem. So my aim today is to explain, to talk about classical field theory and maybe, hopefully, to say a little bit about quantization. But for me, a classical field theory will be one of these moduli problems. So classical field theory on X is such a moduli problem plus some additional geometric structure. So it wasn't right there. So I mean, the moduli problem itself is equipped with additional geometric structure. It'll turn out to be a symplectic form of some kind. Okay, so before I tell you a little bit what this is, I'd like to motivate the definition by starting with the case of zero-dimensional field theory. So, zero-dimensional classical field theory suppose we have a manifold M, which we think of as our space of fields. And a function on it, which we can think of as the action functional. Then classical field theory only knows about the critical points. What does which? Zero-dimensional. So, as we all know, the critical points can be badly behaved and, jump randomly in dimension as a vary f and all this kind of thing. So, I like derived things. So, what I'd like to do, but in fact, what Kapustin and Witten tell us we should do, so we should consider instead a derived critical points. Just because.
Can I read that last sentence? Classical field theory
Say only knows about, or only...
Only knows, only cares.
Yeah, exactly, yeah. Because you're just interested in solutions to the equations of motion. See, I find this rather, it took me a long time to understand this. This is what the battle of physical formalism was doing. It looked like some kind of strange homological machine, but I found it kind of appealing that what they proposed doing in the 70s is what any modern algebraist would want to do now. Just, it's a very natural thing to do. So, okay, so what do we mean by the derived critical locus? Well, I can look at the graph of f inside the cotangent bundle of M, and the critical locus is this graph intersected with the zero section. So the derived critical locus
What is the graph of df?
Yes, graph of df. Well, so we're working again, I think, in this derived world. Algebras of functions on things will be DG algebras, and its space will be determined by its algebra of functions. So we will define the algebra of functions on the derived critical locus. H stands for homotopy. Functions on this by saying, well, I look at functions on the graph and I tensor them over functions in the cotangent bundle with functions on M. Of course, this is how you might define functions on the intersection in algebraic geometry, but we just take in, instead of making this a naive tensor product, we make this a derived tensor product, left-derived tensor product. So,
Can you explain why the naive thing is correct? Why the functions on the intersection over the functions? Is that obvious?
I think it's obvious when you think about it. It's so kind of embedded in my algebraic geometry.
If they were transversal or something?
Yeah, if they're transverse. Let's see. What does it mean to give a function here? You can extend it to one side or you can extend it to the other, and you make them equivalent if they...
Okay.
What is O of n? Is that sort of the sheaf of...
Yeah, say the sheaf
The sheaf of functions, just?
The sheaf of functions, yeah.
Exactly.
Exactly. So let's try and figure out a concrete, this is an abstract way of doing it, but this is a very concrete codunal resolution. So as we know, this is just M is a nice submanifold of the cotangent bundle. We can take a codunal resolution of this as a modulo of this using the exterior powers of the normal directions. So we find that functions on this critical locus looks like the complex functions on M sections of the tangent bundle, cut back in with df, sections of y squared, the tangent bundle, and so on. Okay? oh no, this point is this is what you get at the end.
You're saying what this L means, I mean concretely, I mean this Z, I mean that's,
maybe it might be easiest to think, you know, in algebraic geometry, everything is a polynomial algebra. Then of course this L, you can write it as a bar complex. But it, you know, only we can just replace this guy by some resolution which is flat over this. And when I take the naive conjugal resolution of that tensor, this is what we find. It's an easy computation. So let's rewrite this so we can think of this as functions. While sections of the tangent bundle and its exterior powers, we can think of those as functions of the cotangent bundle. So this is functions of the cotangent bundle, but stuck in cohomological degree 1 of n with the differential. Yeah, I don't know if this helps you. This just means the same thing. So it's sections of the exterior algebra of the tangent bundle. So now let's make an observation. This differential graded algebra has a natural Poisson bracket of cohomological degree 1. How is it defined? Well, it's called the Schouten-Niehaus bracket. So, if X is a vector field, F is a function, then Poisson bracket of this with this. Poisson bracket of two vector fields is our bracket. And Langlands rule determines everything else. So in fact, it's not hard to check that the same will hold. Anytime I have two Lagrangians in a symplectic manifold and I take their derived intersection, you always find this structure. And once more, writing it in this way, so writing it as the shifted cotangent bundle with the differential df, well, the cotangent bundle of the manifold is not just Poisson, of course, it's symplectic. So what this is showing that the derived critical locus of a function is equipped with the symplectic form of degree -1. So what we mean by this, symplectic form is just a closed and non-degenerate 2 form, but just like my functions can be in all degrees, my 2 forms can be in all degrees, and I'm looking at those which are in degree -1. And they need to be cohomologically closed as well.
Do you see the bracket abstractly or just in this model?
I have a kind of fancy abstract definition which uses some kind of ridiculous notions from derived geometry, which works for any two Lagrangians in this symplectic manifold. I don't really have a down to earth and conceptual understanding. Okay, so like what I like to take.
You were suggesting that this is bi-graded. Why is it bi-graded?
it just has this grading.
You said 2 form and degree minus 1, so that's about two numbers exactly the same.
I see, yeah, I see what you're saying, but like, a 2 form is a section of a bundle. But here it's like a section of a graded bundle on some graded manifold. So that section can have various degrees. Like just like I can have a function of degree minus 2. Say like way I can have a 2 form of degree minus 1. So omega 2 of this guy, if this is a cochain complex.
It's like the degree of a polynomial or theory of analog.
Exactly, yeah. I mean, if you think about what's a 1 form, it's going to have pieces from 1 form to the manifold and pieces from these extra exterior directions. And they'll have some cohomological degree. When we write those together, that's going to generate more stuff in here. So we want an element, omega, a cycle, z minus 1. But also that the derived differential of omega is equal to 0, and omega is not invariant.
You have related to is chain one,
Yeah. No.
lost.
Oh.
It seems like there must be a library.
I mean,
two there. So.
Everybody has in their mind the derived difference. Forget about it. The tangent, 1 forms are graded, right? Because this is a graded manifold. Anything I do produces a grading. Therefore, 2 forms are also graded. If I took the whole derived complex, yes, there would be a bigrading. But I'm only looking at omega 2. So the principle, I think, I'm not sure whether physicists will like this, I suspect no, is that to do classical field theory, and indeed to try to quantize, now we don't actually need the action functional. Instead, all we need is the -1 symplectic manifold of the derived critical locus. So this may seem a little funny at first, but it turns out that this data, the derived critical locus as a symplectic manifold, this data determines the action functional up to an additive constant. So, if you took an action functional, you took its derived critical locus, and just took that geometric object, you're not losing much information. But maybe the converse is more important, at least to me, is that if you give me some -1 symplectic manifold, I should think of that as defining a classical field theory, whether or not you've written down it, if you've written it down as the critical locus of an action functional.
In the quantum case, what about the T-plane?
I see, so you're worried about things like things which are constant, locally constant functions. Yeah, well, the formulas I'm working with doesn't really see that stuff. So
What was the question?
his question was, Now, suppose we're doing some kind of gauge theory, you might want to include a term which counts the curvature, this is the quadrilateral class of the connection you're working with. And of course, this won't see that because topological invariants are locally constant. So it's just adding on a constant, effectively. Yeah, exactly. I mean, there's always some kind of ambiguity in the functional measure of a scalar, and that's kind of the same ambiguity. So. Okay, so now I can give you the definition I'd like to use. I hope it's motivated reasonably well. Again, this is only a little elaboration. So classical field theory on X is a formal elliptic moduli problem, like we discussed last time. With the symplectic form of degree -1. Okay, so we need to do a little work to unpack this definition, because we defined these formal moduli problems in terms of Lie algebras. So what we have to work out is, what does a symplectic form mean when we translate between spaces and Lie algebras in this world? So what does a symplectic form mean? Okay, so the answer is actually really nice. I think it was really realized by Quantization 15 years ago. Oh, I'm saying the answer to this question was worked out by Quantization maybe 15 years ago. So I'll explain it. Suppose I have that n be some kind of formal moduli problem. So functions on n.
This would be the derived answer. This would be the derived answer of the symplectic form.
Yeah, that's going to actually be pretty easy. It's just going to become an invariant pairing with the Lie algebra. So, I'll explain. Well, I think it's pretty concrete, right? So we're saying all these fancy words saying around, but it's things you know and love, right? So for functions of the manifold, we can think of as the completed symmetric algebra on V. V is a weighted vector space, and there's some differential on this guy. Well, the Lie algebra associated to it is, I call this G sub n, is V star minus 1. Okay, now we know that if we change coordinates of n, then this equivalence should be canonical, so the Lie algebra shouldn't change, and it changes to an equivalent. homotopy equivalent L infinity algebra.
So that's more. You check the word.
Yeah, you're right. It depends. Yes, if you allow yourself to use nonlinear isomorphisms of L infinity algebras, then it's isomorphic. There's another framework where you can change all the brackets by some homotopies. And it doesn't really matter which one you use. So. But yeah, it's equivalent in this world. There's no difference between this one and the one we get after changing coordinates. Okay, so let's suppose if M is symplectic.
Having trouble remembering from last time. How is V related to that to the elliptic problem?
Oh, what I'm thinking here is like, this is a finite dimensional version. So V is just a vector space.
Okay, so we're going to do closed space first.
Yeah, so we're over a point. Excellent. Just to explain, what is a symplectic form on one of these modular operators. Now, if M is symplectic, then we can choose derived coordinates. So that the symplectic form has constant coefficients. So, well, this T is like a cotangent space at our base point. So it's in wedge to the some degree. Now let's translate this into the Lie algebra. Well, V is isomorphic to the Lie algebra. The dual of V, if V is isomorphic to the dual of the Lie algebra with a shift. Which I can get on. Okay, so that wedge 2 of V is isomorphic to sim 2 of the dual of the Lie algebra with a shift, because as always when we shift things by one, wedges and sims change, so that the symplectic form on the manifold, form of moduli problem, becomes a symmetric pairing on G. It's a non-degenerate symmetric pairing. Okay, so there's a little more data, a little more properties. We also said this 2 form must be a cycle. It's in Z minus 1 omega 2. So the internal differential of this 2 form is 0. So let's call that the internal, as opposed to d to ram. Well, this becomes a statement that we have an invariant pairing on G. Dennis has been suspiciously quiet, which is, you know.
Well, I could ask a question that's burning in my head right now. I mean, the deformation theory by itself is a homotopy invariant of the infinity algebra.
Mm-hmm.
What is the analogous notion with the divisional structure of homotopy invariant? There is a notion. If it's not relevant, you know.
Yeah, I'm not sure. Maybe it's not. I'm not sure how to parse the question. So. Yeah, I like this though because it does tell you, you know.
Oh, it's pretty.
It's pretty. Yeah, it's just come say which came up with this.
Yeah, I remember saying there's no difference between symplectic geometry and Riemannian. I mean, symmetric form is symplectic. There's no difference.
It's a sign, right? It's a shift.
I know what you're doing. Shifty guy.
Okay, so what we're doing is, so we wanted to explain that what is a classical field theory in X. So now we understand. So let's give the more precise definition.
So there's no analog to D derived.
Well, it's a constant coefficient 2 form, so that would be 0. And
Okay, and then non-degenerate.
yeah. So let's be mathematical. And that's the last time we had this idea. So L be an elliptic, say, if e.g. or L infinity, if you like that language. And so remember that this was, so L is a vector bundle, it's a Graham's vector bundle. If we look at sections, called curly L, this space of sections is a DGB algebra, where the differential is elliptic, makes it into an elliptic complex, and the bracket is a bidifferential operator. Okay, so where are we going? So we want to say, what's an invariant pairing on such a guy? Well, so what we need to do is, we should think of an invariant pairing as an isomorphism from G to its dual. So we need to figure out what's the analog of the dual. Now, you could just take the dual of this vector space, but that wouldn't really be the right thing to do because you would end up with, you know, compactly supported sections of something. So it's better to take, we let L shrink in the bundle, which is L star, tensor, say, top forms of X. Then curly L shrink. So this plays the role of the dual. In that if X is compact, L shrink is quasi-isomorphic to the dual L shrink of X, quasi-isomorphic to the dual of L of X. These are homotopy equivalent. But if X is non-compact, you have to worry about compactly supported sections. Anyway, So what should an invariant pairing be? Well, it's an isomorphism from something to its dual. So an invariant pairing so it's an isomorphism of L of x modules. This is getting a little technical, but I think once we write down some examples, it should be pretty clear. L of x modules from L of x to its dual to this kind of adjoint bundle of sheet of x well, firstly, given by a differential operator, but also, we know that if we have a differential operator between two vector bundles, there's something called a formal adjoint, which goes, the formal adjoint involves dualizing the vector bundles and twisting them by top forms. So symmetric means that the formal adjoint of this is equal to D. I hope that wasn't too heavy. So where we can finally make our definition of classical field very precise. So classical field theory, and what we saw was should be an elliptic moduli problem with a form of degree -1. So it's an elliptic L infinity algebraic. With an invariant pairing in this sense. And something a little funny happens with the grading, and there's various shifts. So this must be of degree -3. Maybe I will explain why this happens. So this degree -3 corresponds to symplectic of degree -1, just because when we passed from the moduli space to the Lie algebra, we shifted things around by 1. So this -1 becomes a -3. Is this really cryptic, or?
You said we shifted by -1, so -1 became -3.
Oh, because it's a pairing, right? It was in sim 2. We shifted things by -1, that's a 2.
And the other thing is, if it's a classical field theory, should we know some examples?
You will know, well, yes, I was about to write down examples. Okay, so if a physicist
So
was,
this is 3 of string theory.
yes, and it's also the 3 of Chern-Simons theory. Why does Chern-Simons theory work in dimension 3? Because of this.
Are there other clues there?
Yeah. Okay. So what I'd like to say is that, if you were a physicist, you might come by your field theories by writing down an action function of taking their critical locus, their derived critical locus, and you would produce one of these. But I'm more of a geometer, more geometric bent. I'd like to write down field theories because there are natural moduli problems which have natural symplectic forms in them. So the first example Chern-Simons. So if X is a pre-manifold, well, so if G is a Lie algebra with an invariant pairing, then I can look at the derived complex of X with coefficients in G, and this controls the moduli problem of flat G bundles. And you're deforming the trivial one. Just like I said, you can see that there's an evident invariant pairing of the right degree. Of course, this is in 0, 1, 2, and 3. And
is this M to X?
yes. Those 4 things to erase and rewrite. I don't want to. So the invariant pairing is the pairing between form tensor the algebra element is the integral of alpha 1 to beta times now, clearly this is of degree -3 because it pairs something in degree 0 with something in degree 3, something in degree 1 with something in degree 2. Okay, so say
So E and alpha and beta are in the forms of E and F of the,
these are the Lie algebra parts.
then the graded E algebra.
Right, it's just an ordinary Lie algebra. SLN or something.
Why do you call them E? Are they just elements?
Yeah.
Why couldn't you do this in any?
Oh, well, if you could do this in any dimension, but then if you took an ordinary Lie algebra, you would get a pairing of some degree, whatever the dimension of your manifold was.
Yeah.
So to do it in other dimensions, you can do it, but you have to take some graded Lie algebra with an invariant pairing kind of complementary to the one on your manifold. And that actually turns out to be really interesting. If you do it in dimension 2, this is what Kontsevich did for his Kontsevich formality theorem. If you do it in dimension 4, it's some kind of twisted supersymmetric n equals 4 theory. And these are okay, so what have we got? We have this definition.
Well, wait, you were just suggesting that we just consider a general moduli space almost a general infinity algebra with the degree 3 came up. Now you tell the job you can do other dimensions.
Oh, degree 3 comes out because most of the Lie algebras we like classical Lie algebras have a pairing of degree 0.
Oh.
So if you invented some big graded Lie algebra with it,
Oh.
it's a different degree pairing. It's a little less natural, but you can do it.
Okay.
Where were we?
So there's some graded version of Chern-Simons and other dimensions that you just really grade the algebra?
Absolutely, yeah.
What was it about that?
Well, Martin's talking about this. Yeah.
parts of them come up as parts of supergravity theories and so on, but I don't think there's been a systematic study in these pure topological theories.
Yeah, they have been studied in mathematics, as I mentioned. That considered his original paper in 1994, about transimus theory, where he presents some proof of that you know what is transimus theory. Does it in every dimension above 2. So so Kontsevich in this 1994 paper, he considers this theory in every dimension greater than 2, and constructs the quantum theory. And later on, work about formality of E and opera also uses very similar ideas. So what? Okay. So anyway, so we have this definition. Classical field theory is a moduli problem with a symplectic form. How do we get things with symplectic forms? Well, the most simple and naive thing to do is to take the cotangent bundle of something. So if I have any elliptic moduli problem, then we can consider what I call the cotangent field theory. Defined by, well, to take the cotangent in the world of Lie algebras, we just need to add on the dual of the Lie algebra. So we take L plus the thing playing the role of the dual, and we just shift the degree, so this is in the correct degree. So this is automatically, this has an invariant pairing of root minus 3. So that it defines for us classical field theory.
That's still a Lie algebra.
Yeah, because this is a module.
Oh.
Right? This is a module over this, and the bracket of 2 elements here is 0. And okay, so this construction, this corresponds to T star minus 1 of the formal moduli. Okay. So one thing I kind of wanted to explain is, I've been really struggling to understand things like supersymmetry, or I try to read Witten's papers about what the B model is, or something like that, and you write down these crazy formulas, I can't understand them. But in a lot of cases, all that's going on is you take some elliptic equation you know and love, and do this to it. It gives you a field theory. So let's take a simple example. Let's take the self-duality equation. Where A is a connection on a G bundle on X, which is a form manifold. Well, you can take the cotangent theory this turns out to be what's called self-Julian-Mills theory. It's kind of it's a degenerate limit of Julian-Mills as the coupling constant goes to 0. So another example, see, I have a bunch of ones. So, in mirror symmetry, you have these A and B models, where the A model accounts for more written invariance, and the B model is a bit more mysterious. So let me explain what the B model is. So let sigma be a surface. Actually, I should have said, this is one of the things John mentioned a second ago. Let X be a complex manifold. So the elliptic moduli problem we want to consider is locally constant mass from sigma to X. So what do we mean by this? Well, locally constant means your map must be killed by the Durand differential. So one way to think of this is these are maps of ring spaces where we give sigma the Durand complex X dot complex and the map of ring spaces. But all that's going on is, I look at all first I might consider holomorphic maps, and then I impose the equation that they're constant, that the Durand differential is 0. Then I end up with this moduli space defined by elliptic equations. And if I take the cotangent theory, it turns out to be the model.
You're saying you use df today in this setting, you have to have these forms of that.
What do you mean by df? Oh, do you?
After the function of the manifold with the derived points, the df thing.
Yeah.
So you're
yeah, well, no, it's simpler than that, right? I suppose I need to add on things that impose the equation.
What?
I need to add on, forms are there to impose the equation of flatness, right? So the failure to be flat is in one form, so I add on one form to make that equation hold. Yeah, okay, so there are many other examples, but how much time do I have left? About 5 minutes. Okay. Yeah, which is really a good point of because I don't really have much left to say. I wanted to talk about quantization, but I'm not sure I have much time to get into it. Let's see.
Take 10 minutes.
I have another lecture. What was it? Okay. So now you see that for any system of elliptic equations, you can write down a classical field theory. And what does it mean to quantize this theory? So this is something I've been working on for a while, and I got this definition of what it means to quantize. I've written a book about it in a long paper with Owen William. But so the upshot is going to be, so a quantization of a cotangent field theory gives a volume form on the elliptic moduli problem.
Only of a cotangent?
Yes. And if it's not a cotangent field theory, it's more subtle. It's kind of half density. And in these situations, normally this is a perturbative game. You have to include some power series in h bar, but here in fact the terms beyond h bar vanish. So only the one loop terms contribute. So only the first power of h bar appears. So that we can kind of treat them non-perturbatively.
Because it's usually normalized to the classical terms one over
Yes. Oh, yeah, without normalization, then, okay, only, yeah, you know what I mean, only one loop appears. So we can be treated, in principle, so, I think this is an interesting program which you have many examples of field theories of this nature. Many of them are mathematical and physical interest. Can we compute them non-perturbatively? And as I mentioned in the first lecture, one example I know how to do is if you consider the maps, holomorphic maps of an elliptic curve to some complex manifold, then you can quantize a theory and find that the Witten genus is the volume of the resulting elliptic moduli space. Okay, so maybe I'll end just by saying a little bit, what does it mean to quantize? And then we'll start again from there next time. So if this, like the algebra has an invariant pairing, degree -3, then cochains on this Lie algebra are, I should think of this as being functions in the corresponding moduli. And this object has a Poisson bracket of degree 1. So if this is one of these elliptic Lie algebras on a manifold, if I have an open subset of X, I can consider cochains on L of that open subset. And the definition of quantization is very like deformation quantization. I want to deform this in a way which the first order gives you the bracket. So roughly speaking, quantization is a differential on an H bar such that, say, D is equal to the original differential mod H bar. And the failure of this guy to be a derivation is measured by the Poisson bracket. Okay, so to give a quantization of the theory is to give one of these in every open subset in a way compatible with the natural maps as I vary my subset. So we stop there. What I'd like to explain next time is why such a quantization. Say a little more about what quantization is, and why such a quantization gives you a volume form on a moduli space, and how you can construct these quantizations by abstraction theory. So often there's a completely unique quantization.
Wait, so where is the invariant pairing here?
It's in the Poisson bracket. Like the Poisson bracket belongs to the duos.
On the general case, you could hide things
Here in this equation,
beyond the bracket.
this is it, but the d might depend on h bar as well. I mean, we also have the equation d squared equals 0, which has constraints at all orders of h bar. Okay, so I'll stop there and pick up again.
Well, we had